also A, what else? D, E. Brilliant. All right. They're all fat-soluble vitamins. So if you consume, as I said before, a whole bunch of leafy greens, a big bowl of kale or whatever, you got lots of vitamin A out of it, your body uses this much of it, the rest of it gets stored in your fat cells, okay? Vitamin C, however, is a water-soluble vitamin, which means that anything that you consume that doesn't get used up by your body then gets excreted, okay? So it gets dissolved in water and then works its way through. All right, so vitamin C has to be, should be consumed on a regular basis, like every day you should have your vitamin C. You can save up your vitamin A, but not your vitamin C.
If you had like a year's supply of vitamin K that you ate in like one day, can you just not have vitamin K for the rest of the year?
I don't think so. I don't think your cells will last that long.
You just die.
No, you would just die, no. I don't think so. Okay, so gases in solution. Now we talked about gases and temperature, and that's going to come up on another slide here. But just in generally speaking, gases staying dissolved in solution, the larger gases are going to stay dissolved more easily than those with a smaller molecular weight, just because, as we learned in the last chapter, bigger molecules are going to have a little bit more London dispersion forces going for them. Okay? And now it says solubility of liquids and solids doesn't change appreciably with pressure, but the solubility of a gas in a liquid is directly proportional to its pressure. So what we're saying then is, for example, soda is pressurized when they put it into bottles or cans because they have carbon dioxide gas in the soda and they want it to stay dissolved, okay? So they put some pressure into the solution and pressurize the can to keep the gases dissolved in there. But the pressure is not going to, changing the pressure over a solution is going to affect gases in a liquid, but not a solid or a liquid in a liquid. Okay, and Henry's law is talking about the solubility of a gas is equal to a constant, another K constant, it's Henry's law constant, times the partial pressure of the gas, okay? So then if we increase the pressure over the gas, what's going to happen to this is a constant, it stays the same. What's going to happen to solubility? It's going to go up. So the greater the pressure over the solution, the greater the solubility of the gas in the solution. Okay? And that's Henry's law. Okay, we looked at this chart the other day also, so I'm just going to go over it really quickly. But these are a bunch of different solids, different ionic compounds dissolved in water. And I don't know if you can see it from where you're sitting, but does anybody remember the units for solubility on that graph?
Grams of salt and 100 grams of H2O.
Grams of the salt to 100 grams of water. Good. Okay? And we also said that as temperature increases, for the most part, what happens to solubility of ionic compounds? Most of them increase, okay? Which is the exact opposite of what happens with gases. And this is the other graph that we looked at the other day. Typically, the greater the temperature of the solution, the less soluble the gas is going to be in it. And we talked about the fact that on a warm day, if you open up a can of soda, it's going to go flat a lot more easily than it would if you had it at a colder temperature. Also, it says here, warm lakes have less oxygen dissolved in them than cool lakes. Okay, so for fishing purposes, would you rather be fishing in a warm water?
Yeah.
No,
Or-
they might die.
I don't know. Yeah.
Warm water is when they want to come. Well, if it's cold.
Different kinds of fish live in different kinds of waters.
Like if it's really warm, they want to go around to the bottom.
No,
to like cool down. If it's really cold, I
It's
want
like-
them off to get heat.
no. Like it'd be really hard to get fishing pole through the ice if it was cold though.
Well, that is true. You would have to cut the hole in the ice first. But anyway, that's a topic for another day. Okay, so now ways of expressing concentrations is the next section. A lot of what we did today so far, most of that has been review. And so is some of this as far as expressing things in concentrations. What have we used so far as units for concentration in solutions in this class, Alex?
Molarity and molality.
Molarity and molality, okay? All right, and those are two of the ways that we're gonna look at today also, okay? And then another way that we haven't done yet is called mass percentage, okay? And mass percentage, this is the formula for it, the mass of the solute in the solution divided by the total mass of the solution, and I'm underlining that for a reason. And we're gonna work out a problem on mass percent, which is number 34 in your book, and that is on page 567.
Nobody?
567. First of all, would this even happen? Would iodine dissolve in carbon tetrachloride?
Yes. No,
Why?
they're not polar.
They're both what?
Non-polar.
They're both nonpolar molecules. Good. Okay, so the question says, what is the mass percentage of iodine in a solution containing 0.045 moles of iodine and 115 grams of carbon tetrachloride? Okay, so the solute then we would consider to be the iodine. Okay, and the solution then is going to be made of what?
The CCl4.
Carbon tetrachloride?
Yeah. Gordon.
That it?
Yeah.
And the iodine.
Oh, you mean total? Okay.
Total, okay? We can't forget the whole solution. All right, so what's the first thing we're gonna do?
Convert moles to iodine.
Convert moles of iodine to mass, okay? So 0.045 moles of iodine, and 1 mole of iodine is, what?
126.90.
How much is it?
Times 2.
One.
253.8.
Say that again?
253.8.
253.8
253 and
grams, okay? So changing moles to grams of iodine, do it real quick.
it's from 50.
1.77 times 10 to the -4.
Grams of iodine?
You okay?
11.42 grams of iodine, okay? What's the next step? We know how many grams of iodine, that's our mass of A.
Add that one. Add to the solution and find your total mass.
Okay, so we need the total mass of the solution. The total mass of the solution is going to be 11.42 grams of iodine plus 115.0 grams of the carbon tetrachloride.
That's gonna be 116.42. Oh, yeah,
Oh, well, I'm sorry, and then times 100. So
it is.
Y times 100. Oh.
we're doing mass percent. So it's the mass of the solute, okay, the iodine, 11.42, divided by the mass of the entire solution, and then times 100. That'll give us a percent. Mass percent of iodine would be percent iodine. Easy?
So there would be 9.03 grams of iodine in 100 grams sample of.
Yes.
I state obvious things.
Probably would be 2.
Okay, so the next type of percent solution is something we're going to use when there are very small amounts of solute in a large amount of solvent, and that's parts per million and parts per billion. And if you ever look up air quality or anything like that, and you want to, they'll measure the number of particulates in the air, they'll give that to you in parts per million or parts per billion. Excuse me. If you are looking at water from a lake, if you were like an environmental chemist or something, and you were looking at water in a lake and you wanted to find out concentration of, you wanted to find out the concentration of a substance that's in the lake, that would be measured in like parts per million or parts per billion, because there's not a lot of stuff in there compared to the amount of water that's in there. So the next part of that problem, 34b, says what would be the it says seawater contains 0.0079 grams of strontium. What is that? 0079 grams of strontium ions per kilogram of water. Okay? And then it says, what is the concentration of strontium ions measured in parts per million? All right? So the first thing we're going to do is say, all right, so the mass of the solute is going to be what?
0.0079.
Okay, yeah, so it's going to be the 0079 grams of the strontium ions, okay? And the total mass of the solution is going to be what?
Is that just 1 kilogram?
That was the mass per kilogram of water.
Oh,
So a kilogram is how many grams?
1,000.
1,000.
So it'll be 1,000.0079.
1,000.0079 grams total of solution. Okay, and if you plug in the numbers, don't forget to multiply by times 10 to the 6th.
So it's basically just like a percentage, but doing leaving it in millions. It's just like doing the percentage, but making it.
Yeah, it's exactly like it, except that parts per million is going to be times 10 to the 6th, and parts per billion is going to be times 10 to the 9th instead of 100. Okay, instead of multiplying by 100. And anybody have 7.9 parts per million?
You have 30 seconds, guys.
Sorry, that's a stray mark. Okay? Easy?